when I was drawing this, you were really getting at that. I don't know, is there anything else to say about that? Are you all comfortable with that? Okay. So we're ready. Derivatives, dot products, plug in, we're done. So what is the derivative of that? Should be nice. Now, do you all see right now what really isn't going to matter at all? These aren't going to matter, because when we dot them, we get 0. And that's why we were talking about, does the going around even matter? Really, just the vertical displacement matters. The reason why you can see, hopefully you can see from this, the reason why the vertical displacement is the only thing that matters is because when you dot these two together, if you're talking about gravity, two of your components are always 0. So that when you dot, your last component is the only thing that's going to matter, which is your z component, which is your up and down. Right? So let's go ahead and take our derivative so we have it. The derivative of that is negative 20 sine t, 20 cosine t, and then a constant, right? 90 over 6 pi. All right, we should have integral. It should go from 0 to 6 pi. It should be the vector field evaluated along the curve. So that means we're going to replace x's with this, y's with this, and z's with this, right? But there are no x's and y's and z's. So 0, 0, negative 200, dotted with negative 20 sine t, 20 cosine t, and then 90 over 6 pi dt. And then you multiply, and when you multiply, you get this times this, right? Which is going to be, what, negative 18? Is that negative 1800? No. Is it 18,000? 1800. No. 6 pi. Integral 0 to 6 pi dt. See, this is where my brain is going. 9 times 200 should be 1,800. 90 times 200 should be 18,000. Okay, so this times this, right? Everything else is gone. And now antiderivative of this is a constant, right? So negative 18,000 over 6 pi t evaluated from 0 to 6 pi. And what happens? You get negative 18,000. Work is measured here in foot-pounds. Foot-pounds. So negative 1,800 foot-pounds.
Now, assuming the gravitational field is hanging under and weighing down, like,
Pardon me?
like let's say we're not a man on a silo.
Yeah.
Same thing, it's sideways. If gravity's down sideways, the work will be different.
Oh, yeah. Oh, yes, absolutely. Absolutely. Yeah, if your field stays the same, but you orient that curve differently, it's going to be a different work. Yeah, absolutely. If it's the Leaning Tower of Pisa, right, it's going to be a little different because, I think you get it. Okay, let's see. I think there's one more example. I like this next example because it makes you think a little bit about things. Oh, there's a problem in the book that I think I took this one from the book and I adapted it a little bit, but there's a problem in the book very similar to this. And then in the next problem, they say that as he's walking up the silo, his paint can is leaking. And so by the time he gets to the top of the silo, the paint can is empty. Right when he reaches the top, the last drop comes out. So it's like he starts out at the bottom, it's 200 pounds, right? But by the time he gets to the top, he's 180 pounds. So that changes your vector field because it's not 200 always. It's 200 and then it starts tapering off. It's a good problem.
Would it be in a linear rate?
it would be at a linear rate. You have to actually come up with what that is, and then when you dot, it's, same story. So I think I worked that one out on video. I may not. I don't remember. That's the z. Well, no, the z component of the field would be the only thing that's impacted by that. Okay, look at this one. A 10 kilogram object moves with a position function r of t is sine 4t, sine 8t, t squared, where t is between 0 and 1. Find the work done on the object during this time period. Okay. You've got this object. It's moving along some weird path. And we're trying to calculate the work. What's different about this problem than the previous one? We don't have F. In the previous problem we had F, didn't we? Because it gave us the weight. And the weight meant that the man was on Earth and that the force of gravity, right? The acceleration of gravity was what it would be on Earth. This object right here, it's not on Earth. In fact, we're not saying it's under any influences of force right now.
So all you're giving is the mass.
All we're giving is the mass. So I'm trying to imagine this object moving out in space where there's no acceleration of gravity on it. All right? It's free of any gravitational force right now. I just don't want you to think about this object like on Earth moving. Because if gravity were there, then we would just give you the weight. So what we need to do is find the integral over c of f dot dr. Now, we know that this is f evaluated at r of t dotted with r prime of t. The good news in the problem is that I already know the limits of integration, right? 0 to 1. I already know what r of t is, so I know what to plug in. And I already know what r prime is because I can take the derivative of that.
So,
all I need is the actual force.
yeah. So can we find out that by plugging 1 into the r function to find the total distance, and then we know that acceleration is the derivative of velocity.
Ah, okay. Yeah, there we go. Now you're on. I don't know about the plugging in 1. We don't need that.
Okay.
But you have the right idea. If you're given a position function, right? The first derivative is velocity, and the second derivative is acceleration. And if I gave us the mass times acceleration is force. So we can use that here. We can use that force is equal to the mass times the acceleration vector. Now, the velocity vector function will be the derivative of this. What is the derivative of that? 4 cosine 4t, 8 cosine 8t, and then 2t. That's the velocity function, right? Given a position function, the first derivative is the velocity function. That also happens to be this, doesn't it? We'll use that. I mean, that is also r prime of t. But in terms of what we learned about position of objects, that's the velocity. Acceleration function is the derivative of that, which will be negative 16 sine 4t, and then negative 64 sine 8t, and then 2. Agree? All right. So let's go back up here to force equals mass times acceleration. What we're really saying is that the force is a function of t, and it's the mass, which is 10, times the acceleration function, which is all this stuff down here. And just that 10 out there just is a scalar multiplication. Just scale everything out. So I now have a force vector function. My vector function for force is the vector negative 160 sine 4t, negative 640 sine 8t, and then 20. So when I come in here, right, and I try and evaluate this field at r of t, I don't actually have to plug in r of t. I've already done that. My field is a function of t, isn't it? My field is already a function of t. So I just need to take this and dot it with the derivative, which I just erased. Okay, so let's go ahead and set that up. I think we're ready. Any questions on where this capital F comes from? I'll leave it. Okay, we're doing the integral. We're going from 0 to 1. We're going to take negative 160 sine 4t, negative 640 sine 8t, and then 20. And we're going to dot that with the derivative of the original position function, which was 4 cosine 4t, and then 8 cosine 8t, and then finally 2t, and then all of that integrate with respect to t. Shall I continue? Okay. All right, when we dot this, we're going to do integral 0 to 1. Okay, dotting, we just multiply. So those two multiply together. Negative 640 sine 4t cosine 4t. Okay, next multiplication, these two together.
Hold on, I'm turning on my TI.
Okay, who's got that for me? It's minus, right?
Yeah.
Did I work? Y'all are quick with those calculators, let me tell you. What do you got?
5,120.
5,120. What? Sine 8t, cosine 8t. And then 40t. dt. Okay, I'm thinking I want to integrate this. I kind of like the identity idea at this point right now, using this identity that sine of 2t is equal to 2 sine t cosine t. That I can actually use this identity in reverse if I just half this. Anywhere I see sine t cosine t, like the same argument here, I can replace that by 1/2 sine of double that angle. So I see my sine 4t cosine 4t. I can replace that with 1/2 sine of 8t. And half of 640 is 320, right? So I'm not integrating yet. I'm just using some identities to make my integration a little easier. So this is going to be integral 0 to 1. Half of that, negative 320. And then sine 8t. And then minus, now same thing here. Half of 5120 is 25.
2,560.
2,560. But then sine of 16t, because it doubles the angle, and then plus 40t. So still no integration yet, just identities to help me. And now I'll integrate. What is the antiderivative of sine of 8t? Negative 1/8 cosine of 8t. So when I bring in a negative 1/8 and hit that, so divide that by negative 8, and you're going to get what? 40? So we're going to have 40 cosine 8t. And then same thing here. Antiderivative of this is negative 1/16 cosine 16t. So divide that by negative 16, somebody please. 160. What is it? 160. Okay, 160 cosine 16t, and then antiderivative of 40t is 20t squared. And I'm evaluating that 0 and 1. Almost done. If we plug in 1, we'll get something. If we plug in 0, we'll get something. So what happens when we plug in 1 for t? 40 cosine of 8, whatever that is, 40 cosine of 8 plus 160 cosine of 16 plus 20. Then when we plug in 0, cosine of 0, right, when I plug 0 in here, I get cosine of 0 is 1, so that's 40. This will be 160, and this is 0. So whatever that number is, I believe if I remember correctly, because I did this problem earlier, I think it all comes out to be like negative 339. Somewhere around there, approximately negative 339. I could be wrong, but I'm pretty sure that's what it was close to. So the work done would be negative work. All right. Well, it's taken us basically the better part of 2 days, but we are finished with 13.2. There's your homework. Oh, do you need more time there?
Yeah, that's fine.
5, 4, 3, 2, 1. Okay, here we go. We've made it to the fundamental theorem of line integrals. There are a couple of theorems in math, in your math sequence that have been important. The fundamental theorem of calculus, right, in Cal 2, which related the derivative and antiderivative together. There was several versions of it, but this is the one that most of us are aware of, the one that's the substitution theorem, which basically says that if you have some function and you're trying to figure out the area underneath its curve between a and b, that is going to be equal to the antiderivative evaluated at the endpoint minus the antiderivative evaluated at the other endpoint. Yes? So I want us to understand this visually. If I take the function f of x equals x, right? That looks like this. And let's just go from 1 to 2. If I want to know that area, according to this theorem, what I need to do is take a look at its antiderivative. Its antiderivative, capital F of x, is equal to 1/2 x squared, right? That's my version of 1/2 x squared. And this area in here is equivalent to taking 2 and plugging it into this function, which we would get what if we plug 2 in there? You get a height of 2 here, right? And then you plug 1 into this function. What would you get if you plug in 1? You get 1/2. And if you take that 2 and subtract that 1/2, which really means the distance between these 2 points, right? These 2 heights, that distance, 2 minus 1/2, 3/2, is equal to the area of this piece over here. Quite remarkable, but that's the connection. The heights of the endpoints on capital F, the difference between those 2 heights corresponds to the area underneath this curve. That's the fundamental theorem of calculus, Cal 2. There's also a fundamental theorem of algebra. You all ever hear about that one? Fundamental theorem of algebra? I don't remember when I was a student, I don't remember when I was in college algebra ever hearing about the fundamental theorem of algebra. I really didn't hear more about it until I got into complex variables. And the fundamental theorem of algebra says that if you have a polynomial function of degree n, that you're guaranteed to have n solutions, as long as you're allowed to have complex solutions. Complex solutions are allowed. And so that's why you don't hear too much about it in college algebra, because you have to bring in the complex numbers for that fundamental theorem of algebra to be good. All right, so now we move on to the fundamental theorem of line integrals, which is quite remarkable. It says the following. If C is a smooth curve given by some vector function r of t, where t is restricted between 2 points A and B, so we've got this curve, C. Right here, this curve is also given to you by r of t. So if we're going in this direction, this endpoint right here is r of A, and this endpoint right here is r of B. So if you plug in A into this, it would spit out this point, right? It would actually spit out the vector that points to that point. And if you plug in B into this curve, it's going to spit out that one. Understand? Yes, yes, yes? Okay. So if you've got this scenario, and f is differentiable, so you've got this curve, and you've got this scalar function that is differentiable. Okay? Scalar function that's differentiable, such that the gradient of that scalar function is continuous, meaning that when you take the gradient vector, that vector is well behaved, doesn't do anything crazy. Then this is true. The line integral over C of the gradient of f, remember the gradient of f is a vector, dotted dr, so isn't this work? This is the work done over the gradient vector field, is equal to the scalar function evaluated at r of b minus the scalar function evaluated at r of a. That means, you see that point right there? That's a point. You just plug it into the scalar function and then subtract from that this point into the scalar function. You take those two numbers and you subtract them, and that is the value of the work done. Do you kind of see a little bit of a similarity between what we just wrote up on the board? Integral a to b, little f of x dx equals capital F of b minus capital F of a. Okay, let's see the similarity. What's the relationship between capital F and little f? This is the antiderivative, which means the derivative of this is that, right? Yes? The derivative of this is that. And we're evaluating at the two endpoints. Over here, I have little f, right? What's the thing inside the integral? The derivative of little f, right? It's the gradient. So you have this is almost like your capital F and your little f. And then it says you evaluate at the two endpoints of the curve. So you should see a similarity in these things. This theorem says that the line integral of a conservative vector field is simply the difference of the value of the function at the endpoints. Further, the line integral on any two paths that connect the same 2 points are always equal. Okay. We're going to have to see this in action.
On the differential definition, if f is continuous, does that imply that the gradient is also going to be continuous all the time? Or is there a check for that?
There's not a check. This theorem has certain conditions on it, right? F has to be differentiable. The gradient has to be continuous. The reason we have to put that in the theorem is because if someone generates a function that somehow is differentiable but has problems with continuity, the proof of the theorem breaks down. Now, I'm never going to give you one of those, but you can't just say it's always true. Because some skeptic will come out there and they'll come up and they'll say, you know what, here's a function that's differentiable, but hey, look, its gradient's not continuous and your theorem falls apart. So you have to state that in the theorem, that the continuity is needed for the theorem to hold. But you don't need to worry about me giving you something where that wouldn't happen. All right. This should be, well, we'll get through this one. So here's a scalar function, right? That's a scalar function, x squared plus y squared. And c is given by r of t equals t sine t, t cosine t on the interval 0 pi. Find the line integral over c of the gradient vector field of f with respect to r, with respect to the curve. That's work, right? That's work. But the gradient of f, that's our field, needs to come from here. So what is the gradient of f for us? 2x, comma, 2y. Done? Yes? All right, and we have our r, don't we? So I need r prime. What's the derivative of this?
Didn't you say you can just substitute?
Yes, but I don't want to do that.
Then why did you?
Because I want you to appreciate it. Okay? I'm not going to do the whole thing. I'm going to start doing it, and then I'm going to say, wait a minute, what does this theorem tell us, right? Okay, so look, what is the derivative of this going to be?
Sine t.
Yeah, so we have to do a product rule here, don't we? So that'll be sine t plus t cosine t, and then cosine t minus t sine t, and that's our derivative, right? I'm supposed to take that and dot it with this, right? But replacing the x and the y with what?
T sine t.
I replace this x with t sine t and this y with t cosine t. So if I'm just kind of blindly going through this integral, I would have integral 0 to pi, right? And then I would have the gradient vector field evaluated along my curve, which would be 2t sine t, and then 2t cosine t. And then I have to dot that with the derivative, which was sine t plus t cosine t, and then cosine t minus t sine t, dt. No big deal, right? I just dot those together then. This is starting to get pretty ugly, isn't it? It's starting to get pretty ugly. But let's keep going. Okay, so if I dot this, I'm going to go here to here. So let's see if I can't do that. It is integral 0 to pi. What do we have here? 2t sine squared t plus 2t squared sine t cosine t. Gosh, I'm really hoping for cancellation here. And then this right here plus 2t cosine, it's t squared. Wait, I'm doing this one right. Yeah, just cosine. Oh, okay, I thought you were saying square the t. Okay, cosine squared t, and then minus 2t squared sine t cosine t. Done. dt. I do get cancellation. This one and this one. Oh, this isn't so bad.
And then you have an identity.
I have Pythagorean identity in there. Don't I?
Yeah.
So I can take this one and this one. I can factor a 2t out, and it becomes 1, doesn't it? But then I still have 2t. So now my integral is 0 to pi of what? 2t dt, which is t squared, evaluated, 0 pi. Answer is pi squared. Okay, well that wasn't so bad. but we didn't use the theorem at all in this. We just ground that problem out, didn't we? We got kind of lucky that everything worked out for us here. Let's instead use the theorem. The theorem says that if C is a smooth curve and f is differentiable and the gradient is continuous, then if you take the gradient and dot it, right, dr, and you do this integral, then you don't actually have to do that. All you have to do is take the curve, the scalar function, and evaluate it at the two endpoints of the curve, and that subtraction, that's your answer. Sorry, I'm spitting over here. Just so excited. Okay, so look, we have this. We need to figure out what the endpoints of this curve are. Can we find the endpoints?
You just have to plug in 0 and pi.
Yeah. So what is r of 0? Plug in 0, you get 0, 0. So okay, 0, 0. All right. Now what is r of pi? Well,
Pi.
sine of pi is 0, so that's 0. And then what's that?
Negative pi.
Negative pi. Sorry, I forgot to put the 0. 0 and then negative pi, right? Like this? Okay. Those are the endpoints. According to this theorem, since we're doing the gradient of f, right? This should just be f evaluated at the endpoints here. That means evaluated at r of pi, and then minus r f evaluated at r of 0. Okay? But that just means you take f and you evaluate it at r of pi. R of pi was the vector 0, negative pi. And then you take that, subtract f, evaluate it at the vector 0, 0. What does it mean to plug a vector into a scalar function? X is 0, y is pi. So let's plug that in. What happens if I plug in 0 for x and pi for, or negative pi for y? You get pi squared. And what happens if I plug in 0 and 0? Get 0, so the answer is pi squared. Right? This only works if the piece in here is the gradient of a scalar function. If it is not, you can't do this. Yes?
Would we use this in 13.2 example 6?
In 13.2 example 6. I don't know. I don't remember it. Could we have used this one? Yeah, I don't see. Well, we were asked for the work. Yes. Yeah, we could have. We know what little f is. We were asked to find the work done by the gradient vector field. So yes. Now we couldn't do it. We couldn't do it here because we don't know if this f right here is the gradient of a scalar function. We don't know that. We don't know that. Okay, so let's see if you remember anything from last class. If this is the gradient of a scalar function, then this vector field is called conservative. So I don't know if that's a conservative vector field or not, so I can't use the theorem. And that's where we're headed now. I mean, I know I only have 5 minutes, but let's see what else we can talk about. So path independence, this is a theorem. Look, let's say our curve is closed. What if we have a curve that starts at point A and ends at the same point, right? Let's say we have that. A nice closed curve. Then we say that the work done, okay, is path independent in D if and only if that is equal to 0 for every closed path, every closed curve in C. I think this is a good point to end. It's going to take a little bit of explanation. But I can get you to start to think about it. If I'm trying to integrate over a closed curve, right? Let's say that the vector field I'm integrating over is a gradient vector field. Then it's just the first endpoint minus second endpoint, right? And if it's the same point, then the answer should be 0, shouldn't it?
Yes.
But that only works for gradient vector fields, right? Conservative vector fields, that would work. And that's what this theorem is saying, is that if you always get 0 for every closed curve, then we can say that we call it path independent. So it doesn't matter what the path is. Yeah, this is a good place to stop. We'll come back, we'll revisit this.
Because the definition of work itself is based on displacement, so the displacement is just 0.
Yeah.
Well, no, that would be implying that would mean that just because it's a loop, that your work is always 0. That's not what this is saying. What I just said was that if the vector field was conservative, then it would be 0. And gravity is a conservative vector field. So it would work for planets, but but in general you can't say that. Yeah.